Hello and welcome. In this module we will continue the discussion on dispersion in the optical fibers. Let us look at a specific case of how a Gaussian pulse would broaden as it propagates through the fiber. Let us assume that we have a Gaussian pulse at the input of the fiber. This Gaussian pulse can be represented by giving its width, which we will take it to be some 2 times T0, and an expression for this Gaussian pulse will be given as some amplitude. We do not really want to bother about the amplitude. So, let us call this as some psi 0 e to the power minus t square by t 0 square. Okay. So, this is the Gaussian pulse which would be launched in the fiber at z equal to 0. So, at z equal to 0 you are launching this pulse. Let me tell you what we mean by this pulse that is being launched. Actually what I mean to say is that this pulse would not be directly launched. Okay. It would actually be multiplied, or it would be modulated by a carrier, and the modulated pulse can be written as e to the power minus t square by t 0 square times e power j omega 0 t. This omega 0 is the carrier, and this factor, this expression that we have written is how the amplitude of the pulse changes with respect to time. But in addition to this one, there is also a transverse distribution of the pulse itself. So, that is f of x y or equivalently f of r phi, which tells you how the mode is distributed in the transverse plane, right. So, we solved an equation for how the mode would be distributed in the transverse plane. The fundamental mode in terms of r and phi depends like this. So, j 0 of u r e to the power j nu phi, or rather for the fundamental case this will be independent of frequency, but independent of the azimuthal number phi, but this is the transverse field distribution. So, we will assume that this transverse field distribution does not change. So, you have in terms of the transverse plane a Gaussian type of a pulse, okay, or the J0 type of a pulse. Okay. In time this would be varying as another Gaussian pulse. So, there are two different aspects going on. One is in the transverse plane, what is the distribution of the mode energy, that is determined by the solution for the transverse field components, which is essentially what we did in the mode theory, and how a particular mode, that fundamental mode or any other mode, is propagating in with respect to z and time is given by this modulated term, and how this modulated term will evolve through the fiber as it propagates. Okay. So, please keep in mind these two things. We assume that propagation does not change the transverse distribution, the modal distribution of the energy remains as it is as it propagates through the fiber. So, therefore, we do not really worry about what is happening to the transverse plane, because we assume that nothing is changing with respect to the transverse field distribution. The mode pattern remains the same, only in time they are changing as a Gaussian pulse. There is a certain amplitude psi 0, and then this pulse has a certain width which is 2 times t 0. It is also of course modulated by the carrier e power j omega 0 t. Let us describe this one as the pulse at z equal to 0 and time t. Our objective would of course be to obtain psi of z t. Okay. After we have propagated this at an arbitrary distance of z, we want to obtain what is the expression for psi of z t. The easiest way to do this one, which also gives you a numerical way of solving this problem, is to go to the frequency domain. We can go to the frequency domain as long as this amplitude psi 0 is very small, okay, in the sense that you do not excite any nonlinear terms in the fiber, which is quite good approximation for most communication systems, as long as you are looking at a short distance communication. For long distance communication, unfortunately nonlinearities will be there, and this description is not sufficient then. So, for the linear propagation case, we can go to the Fourier transform of this one and then write the Fourier transform of this as, or in fact one can actually write down this psi of 0 t as integral of a of omega or a bar of omega to denote a frequency component or the Fourier transform component times e to the power j omega t d omega. So, I am writing this psi of 0 t, which is a time dependent function, in terms of its Fourier transform. Well, there is also 1 by 2 pi, which we should not forget. So, we can write this psi of 0 t as a of omega e power j omega t. Of course, what is a of omega? A of omega is nothing but Fourier transform of this fellow, right. It is Fourier transform psi of 0 to e power minus j omega t dt, and if you look at what is the situation for this particular time dependent variable, you can substitute this here. The amplitude psi 0 being a constant simply moves out of the integral, and here you have e power minus t square by t 0 square e power j omega minus omega 0 t dt. So, clearly this is a modulated waveform, therefore, first find the Fourier transform of this Gaussian pulse and then shift that spectrum by omega 0 in order to get the modulated spectrum. So, in order to get the Fourier transform of this, if you do that, going back to the tables of e power minus t 0 square by t 0 square, the Fourier transform of that one, what you end up with is some other constants, which let us call it as psi 0 prime, okay, and you have e to the power minus t 0 square by 4 omega minus omega 0 square. Okay. So, the Fourier transform also is a Gaussian function, except that this is now centered at omega 0, which is the carrier frequency, and it has a width which is 1 by t 0 square. So, the larger the pulse in the time domain, the shorter will be its spread in the frequency domain, and we are assuming that this spread in the frequency domain is much smaller compared to the carrier frequency. So, that is an assumption that we are making. Okay. So, this is what your A of omega would look at z equal to 0. Remember, we are still at z equal to 0, we have not yet begun to propagate the pulse through the fiber, we are still at the fiber input. Now, let us try to propagate this one, and here you have to remember from the previous module that I talked about, you have to consider Fourier transform as a sum of many frequency components, each frequency component having a different amplitude, and then visualize the propagation as each of these frequency components propagating along the fiber. When they propagate along the fiber, what will change? They will pick up a phase factor of e to the power minus j beta z, correct. They will pick up a phase factor of e power minus j beta z, and that beta will be different for different frequencies. So, you have a pulse in time domain, you go to the frequency domain, you have a pulse in a frequency domain, right, and this frequency domain picture can be thought of as multiple frequencies. In fact, it would be an infinite number of frequencies between the range, but nevertheless you can think of them as multiple frequencies, each having different amplitude, and then as each of these propagates through the fiber, it will pick up a phase factor which is dependent on what frequency is propagating. So, at the output you simply sum everything back and go back to the time domain by taking the inverse Fourier transform. So, that is all you are going to do. You start with Fourier transform at here, and then you go to the Fourier transform at the, or inverse Fourier transform at the output end. Okay. So, let us do that one. We have already done the Fourier transform part at the input side, and we have seen how the spectrum would look like. Now, I go back to the expression of psi at any z where I want, right. So, this psi at any z after propagating a distance z should be given by the same expression, except that I have this psi 0 prime, which is this constant e power minus t 0 square by 4 omega minus omega 0 square times e power minus j beta of omega into z. This is the phase factor that is picked up by the frequency component omega as it propagates through the fiber. There is also d of omega. Okay. So, I have considered these terms of different frequencies. They all have picked up a certain phase factor, which is e power minus j beta of omega into z, and then I am simply summing everything back, essentially taking the inverse Fourier transform. So, this is all the equation that is there, and if you want to solve, you can solve this using a simple numerical method. You start with the pulse at z equal to 0 with respect to time. You can discretize this. Okay. So, you can discretize this in some n number of points by using some discretization technique, and once you have done that one, you can take the Fourier transform. After you have taken the Fourier transform, to each term you multiply this factor e to the power minus j beta of omega n into z, and then you take the inverse Fourier transform, and what you get here would be psi at z and t n. So, at a different distance, what you get is your function which you were looking for. It would be discrete, you can visualize the continuous expression for the same. So, the core of the algorithm here is this: you discretize, that is, you represent whatever that you want to transmit on a computer by a discrete function, take the Fourier transform, and do not forget to multiply each term by the appropriate phase factor, and then take the inverse Fourier transform. That is all that is there to it. In the assignment, we will give you a code which will enable you to perform this assignment and see for yourself as you propagate the pulse through the fiber, how that propagation would affect the pulse, how the pulse would spread out. So, we will come back, we will give you the MATLAB implementation for that one. You can take a look at that MATLAB implementation later. However, for analytical purposes, let us try to see whether we can take the inverse Fourier transform of this expression. How do I do that? Well, first of all, I need to know how beta is changing with respect to z, right. So, how is beta changing with respect to, sorry, not z, how is beta changing with respect to omega? I really do not know how beta is changing with respect to omega, because it is quite a complicated expression that I do not even have a proper analytical value for that, analytical expression for that. What I know is that the spread of the spectrum, that is the spread of the pulse in frequency domain, the frequency domain bandwidth, as if you would say, is much smaller than the carrier frequency omega 0. Because this is smaller, I can approximate this beta around a frequency, carrier frequency. I can write this beta of omega as the Taylor series expansion beta of omega 0, and then you have plus del beta by del omega evaluated at omega 0 multiplied by omega minus omega 0, plus you have omega minus omega 0 square by 2 factorial, 2 factorial is 2 of course, and then you have del square beta by del omega square evaluated at omega 0, plus so on. These terms are going to be small, so we can neglect them, and this term del beta by del omega at omega 0 in the literature is denoted as beta 1. So, you have omega minus omega 0 into beta 1 plus omega minus omega 0 square by 2 into beta 2. Beta 2 denotes the second order derivative of beta with respect to omega, which is evaluated at the carrier frequency omega 0, and this beta of omega 0 can be written as beta 0 itself. So, this is the approximate expression for beta of omega. I have neglected all the third order and higher order terms. In case this neglection is not good, you can include those terms also. Okay, so, now we have expanded beta of omega, which then makes this e power minus j beta omega z phase factor as e power minus j beta 0 z, e power minus j omega minus omega 0 into beta 1 into z, and there is also this e power minus j omega minus omega square by 2 beta 2 into z. Okay. So, let us put this one into this expression here, and then evaluate the inverse Fourier transform. So, I get psi of z t, the pulse envelope at the input, is given by 1 by 2 pi some constant psi 0 prime, right. So, I am taking that one out of the integral, and what I am left here is e power minus t 0 square omega minus omega 0 square by 4 e to the power minus j beta 0 z e power minus j omega minus omega 0 into beta 1 z e power minus j omega minus omega 0 square by 2 beta 2 z. Now, I remember I have forgotten to include e power j omega t here in the inverse Fourier transform, correct. I have e power j omega t into d omega, this factor I forgot to include. Now, let us include that. So, I have e power j omega t d omega. What we will do is we will substitute omega minus omega 0 by some dummy variable u, okay, and therefore, this gives you d omega equal to du. This integration was anyway going from minus infinity to plus infinity, the integration will remain the same. So, you get psi 0 prime by 2 pi integral e power minus t 0 square u square by 4 e power minus j beta 0 z e power minus j u beta 1 into z, right. For omega minus omega 0 I am substituting u, and then I have e power minus j u square beta 2 z by 2 e to the power j, but what is omega? Omega is nothing but u plus omega 0. So, I have e power j u t e power j omega 0 t d omega. Now, look at this term, this e power j omega 0 t term. Does it depend on frequency? No, it does not depend on frequency. So, you can actually remove this e power j omega 0 t term outside the integration. You can also remove this e power minus j beta 0 term, e power minus j beta 0 into z term, because that is also independent of frequency. Beta 0 evaluated at omega 0 is actually a constant. Therefore, that term can be removed, e power j omega 0 t term can also be removed. In fact, if you remove them, you end up with this equation, which is e power j omega 0 t minus beta 0 into z. This would actually tell you how the carrier would have propagated if it was not modulated. Okay. So, it would have simply told you how the carrier would have propagated if it is not modulated, and this is in fact defining the phase velocity. This is what I meant when I in the earlier module I said carrier travels at phase velocity omega 0 by beta, the carrier is propagating at this phase velocity. So, I have removed this one. So, in this expression I have removed that. What is now remaining can be grouped again together. Okay. So, there are terms which are u square dependent. So, I can group this term with this one. I can write this e power j u of t, e power j u beta 1 of z. So, I can write this one and say psi 0 prime by 2 pi. I am not writing this e power j omega 0 t minus beta 0 into z term, but you have to assume that the term is there. So, you have e power j u is a common factor. So, I can write this as t minus beta 1 into z. Okay. Interesting, I have t minus beta 1 into z, and then I have e to the power minus, first there is u square, then you have t 0 square by 4 plus j beta 2 z by 2. Is that okay? So, this is this one integrated of course with respect to du. So, this is what I have. Now, I can write this t minus beta 1 z, this is the only place where t term is there. So, I can write this t minus beta 1 z as some tau. Finally, I know that the function would actually be with respect to tau, right. So, instead of time it would be tau, and that tau which is given by t minus beta 1 z, you will appreciate this one better if you remember what beta 1 is. Beta 1 is actually differentiation of beta with respect to omega. But remember, we had defined group velocity as d omega by d beta or equivalently del omega by del beta. So, del beta by del omega must be 1 by Vg. So, it is like a group delay, beta 1 is like a group delay happening. So, divided by L will give you the group delay. Okay. So, beta 1 is inversely proportional to Vg. So, you can write this one as t minus z by Vg. So, what you can see is that eventually you are seeing that the Gaussian pulse would be arriving at a velocity which is dependent on group velocity, not on the phase velocity. The carrier would arrive at the phase velocity, whereas the pulse would arrive at the group velocity. What is left here? This is one big term which you can think of as some d square, okay, where d is a constant, because inside if you look at it, t 0 square is a constant, beta 2 is a constant, because that is what we have assumed. You have evaluated beta 2 at that particular point. It is z is a constant because you are looking at a particular value of z, right. So, this is a constant which you can write this as d square, and really what is happening to this equation including this 1 by 2 pi is that you are simply looking at the inverse Fourier transform of this e power minus u square d square term. Okay. If you are not comfortable having u around, since u is a dummy variable, you can simply write this as e power minus omega square d square term, and I know that this is a Gaussian pulse shape, and the inverse Fourier transform should be a time dependent term which would be like e power minus t square divided by d square, give or take some constants are there. There is, if this was divided by 4, then this would have been okay because you have e power minus t square by d square. Since it is not, then you can multiply and divide by 4, and then this would be e power minus t square by 4 d square. Okay. So, the point to note here is that what we have in the bracket here, or rather in the expression for the integral, is actually nothing but simple Gaussian inverse Fourier transform of a Gaussian function. Okay. Rather than calling this as some constant d square, let us be little more clever and call this as t square, but because this would depend on z, I am going to call this as t square of z. Okay. So, I get e power minus t square of z, but at a given z this t square is a constant. So, please do not forget that one, and this inverse Fourier transform will be e power minus t square by t square of z. There is a factor of 4 or something, that is okay, you do not really have to worry about that factor 4. Okay, so this is what we have. Interesting. What is t square of z? T square of z is given by t0 square by 4 plus j beta 2 z by 2. How is t square z a complex number? Well, it is complex because of this j beta 2 term. But what is the implication of this? Let us look at what is the Fourier transform. So, the final result psi of zt is given by all those constants as c. Because there is an inverse Fourier transform, there would be one more constant. So, let us call all those constants as some constant c. Okay. And you have the carrier term arriving here with its own phase velocity e power j omega 0 t minus beta 0 z, and then you have the Gaussian function. But remember now, this was the Gaussian Fourier transform, but it is not this t that I am looking at, it is actually this t minus z by Vg that I have to look at, because this is the Fourier transform of the Gaussian, but t itself is given by t minus beta 1 z, right. So, here it is that. So, you get e to the power minus t minus z by Vg whole square divided by some 4 t square z. This is the Gaussian pulse that I have obtained. Forget about this factor of 4 here. The point here is the pulse width has now become a function of z. In fact, because t square z is this number, you can write this one in terms of its magnitude, call this as Tm square of z, and you can also write this angle. Okay. So, this would be the angle theta Tm of z. Okay. Again, this is a function of z because you are evaluating at different values of z, but if you fix the value of z, this is all going to be constant. So, I can write down this in terms of magnitude and phase angle. So, I can write this fellow as e power minus t minus z by Vg whole square divided by some 4 Tm square z, and then you have angle here which is e power j theta Tm of z. So, this e power j theta m can go on to the top and essentially become a constant phase for you. Okay. So, there is a phase factor associated with this one. So, you can evaluate this one, or you can write down 1 by t square z itself as some magnitude and a phase angle. Okay. In any case, whatever you do, you will see that there is a magnitude and a phase angle that is present, and this phase is a function of z. Okay. This gives rise to what is called as the chirping in optical fibers. Chirping is a phenomenon in which the instantaneous frequency keeps on changing, okay, and that chirping is coming because of this theta Tm of z. A more careful analysis of, by going to the tables of Gaussian function will actually show that this expression which we have written down for t square of z can be written as c by t of z divided by t0 e to the power minus t minus z by Vg whole square divided by t square of z, and there is a phase factor e power j phi of zt minus beta 0 of z. Okay. So, this would be the expression for psi of z and t, taking all these constants. T0 is of course the original pulse width, or there is a square root here. So, T0 is the original pulse width and T of z is the pulse width at any point z. I have just separated them out in terms of its phase and magnitude angles. Okay. So, this phi of zt is basically omega 0 t coming in from the carrier term, plus there is also kappa t minus z by Vg whole square, and because of this t square of z term, there is half tan inverse of 2 alpha z by t0 square, where alpha itself is a different parameter. Alpha is basically beta 2. Okay. So, you can actually see that if you are little more careful in Fourier transform, this is what you are going to get. And what is interesting about this is that at z equal to 0, you might have a certain pulse, a Gaussian pulse, but at a different value of z, the pulse would actually nicely spread out, and this width is given by this t square of z, or rather it is a function of this t square of z. You will also see that if you look at it in terms of its carrier frequency, you will see that, first let me draw the pulse envelope, now let me fill up the modulated waveform. So, the frequency of the carrier is actually increasing. So, this phenomenon is called as chirping. You can look at the assignment for more details, for some careful details about the mathematics involved here. I have just kind of given you the intuitive picture. So, let me summarize whatever we have done here. We said that dispersion is a very important topic in optical fiber, and that is clearly so because it causes pulse to spread out, and once pulses start to spread, then the rate at which you can send the pulses, that is you send in one pulse, you have to wait until the pulse has spread properly, right, because if you send in a pulse before the pulse spreading has been taken into account, then the pulse as it propagates would spread and then it would actually invade into the other pulses territory. So, it essentially starts to talk to the other pulses, giving rise to what is called as the intersymbol interference. So, pulse spreads and gives rise to intersymbol interference. There are many different type of pulse spreading phenomenon, which is the dispersion phenomenon. Material dispersion arises because of the material, waveguide dispersion arises because of waveguide dispersion, or chromatic dispersion arises because of the geometry effect in single mode fibers. Polarization mode dispersion, we will talk about it in a later stage, and then we also have another dispersion which is multi-mode fiber dispersion, that is intermodal dispersion, which anyway does not really figure into our course at this point. When calculating how a Gaussian pulse would spread, the reason we took Gaussian is because it kind of is simple to analyze analytically. You could have taken any other pulse in a numerical method that we will supply, you can actually see that for yourself, nicely Gaussian pulse spreading out or any other kind of a pulse that is spreading out. The idea is you start with whatever the pulse that is given to you at z equal to 0 and then go to the frequency domain picture. So, when you go to the frequency domain, you will get the spectrum and then you propagate each component of that spectrum along the fiber. As this component propagates, it will pick up this e to the power minus j beta of omega z phase factor, and that has to be taken into account. For the case of Gaussian analysis, Gaussian pulses, there is a nice inverse Fourier transform that you can do, and what you essentially see is that the pulse not only spreads out, it's actually its amplitude also starts decaying, right. As you can see when we drew the pictures, the pulse might have started out with this amplitude, but as it propagates its amplitude decays, also its frequency changes, there is a chirping that is going on, and this chirping depends on sign of beta 2. If beta 2 is positive, right, corresponding to what is called as a normal dispersion, then there is a spreading of the pulse. However, when beta 2 is negative, then the pulse initially contracts, okay, and then of course begins to spread again. So, this kind of a behavior of pulse initially contracting and spreading, there is a region in which the pulse is actually getting shortened, is called as anomalous dispersion, and that happens when the sign of beta 2 is negative. So, all these problems do occur. In addition to just pulse spreading, you also have what is called as chirping, and one has to take care of these factors when designing an optical communication system. So, we will stop here and we will take up the question of additional things, additional factors that affect the design of a single mode optical fiber, such as attenuation and nonlinear effects in the later modules. Thank you very much.